All right, welcome back. So this week we are going to be doing some practice problems with simple machines, work, force, and mechanical advantage. And these will be great for getting you all prepped up so that you know how to do these problems for your Rube Goldberg machine and for a quiz that we have coming up on work, force, and mechanical advantage and simple machines. So let's start by jumping in, and we're going to do a few of these little practice problems. So there are 15 total problems that I've got posted for you, 3 pages worth there. And I'm just going to go through and do the first few together so that we can think about how we go about doing them. So remember, you will want your physics everything sheet with you, especially, hint, hint, page 2 of your physics everything sheet. On page 2, it has helpful equations that you can see on the whiteboard behind me, such as work is equal to force times distance, potential energy is equal to mass times acceleration due to gravity times height, kinetic energy is equal to 1/2 mv squared, real mechanical advantage is equal to the force of the load divided by the force of the effort, and ideal mechanical advantage is equal to the distance of the effort divided by the distance of the load. Okay, so let's get started. The first one, the circus has come to town and has a new show involving an elephant and a hippo. The 2 mammals are trained to balance on a seesaw. If each animal starts at a position 2 meters from the fulcrum, the seesaw won't balance. At what distance from the fulcrum should the hippo stand to make the seesaw balance? Okay, so the hippo, it's asking at what position the hippo should stand. So how far should that be? And since it's a distant as a far, right, that's going to be a distance. So I want to know the distance of the hippo. So I'm going to call that d sub h. Now I see down below, I have 900 newtons, and I know that newtons is a force, so that must be the force of the hippo. And then I also have a force of the elephant. The force of the elephant is equal to 1100 newtons. And I know the distance of the elephant too, because it says it's 2 meters from the fulcrum. So that distance right there is 2 meters. And that's going to be the distance of the elephant. So I've got forces and distances. All right. So I need an equation that has forces and distances. And I see that my first equation is work. Now, it doesn't actually ask me to calculate the work. It asks me to calculate a distance. But remember, because this is a seesaw, I could set it up like this. And I could say on this little seesaw, I have the work on one side, right? So I'm going to call this the work on the elephant side has to equal the work on the hippo side, or the energy on each side has to balance. I could phrase that again as the force for the elephant times the distance for the elephant has to equal the force for the hippo times the distance for the hippo. Now I just need to plug in those values. The force of the elephant is 1100 newtons. So I'm going to do 1100 newtons times the distance of the elephant was 2 meters equals the force of the hippo, that was 900 newtons, times the distance of the hippo, and that's what I'm trying to solve, d sub h. There you go. All right, so to get it, get the distance by itself, I have to divide both sides by 900 newtons, divide by 900 newtons. That'll cancel, and I'll be left with 1100 times 2 divided by 900. I'll need to use a calculator for that one because I have forgotten my 11/9 timetables. 1100 times 2 divided by 900 gives me 2.44 repeating meters. Now, in this case, all of my numbers are like one significant figure, so I could round it to 2, but that's not specific enough. I'm going to round it to 3 significant figures because I have 900, 900, and for the significant figures, I want to use the smallest value, but that would be 2 meters, and that just doesn't feel like enough. So I'm going to kind of break my own rules and say that the distance of the hippo should be 2.44 meters from the fulcrum. There you go. Excellent. Okay, let's do number 2. In the diagram, if the distance from A to B is 20 centimeters and the distance from A to C is 80 centimeters, so I'm going to start marking this guy up. A to B right here, that is 20 centimeters. A to C is 80 centimeters, okay? What is the mechanical advantage of the lever? So I know, oh, and it says assume B is the load. Okay, so B is the load, so 20 centimeters, that's the distance of the load. 80 centimeters, that's the distance of the effort. And I need the mechanical advantage. So I have 2 equations for mechanical advantage. They're both behind me. I have mechanical advantage real, which requires a force of the load and a force of the effort, but I don't have any forces. So this one's not going to do anything for me because I don't have the forces to put in. And then mechanical advantage ideal. So I'm going to do mechanical advantage ideal because I have a distance of the effort divided by a distance of the load. All right, so the distance of the effort over the distance of the load, I can plug in those values. That would be 80 centimeters divided by 20 centimeters. And in this case, I didn't convert it to meters because I have the same unit on top and bottom, so it's going to cancel the unit anyway. So that will leave me with an answer of 4 for my mechanical advantage. Or I could say that's 4 times easier. Right? So my mechanical advantage is 4. Okay? Or 4 times. Nice. All right, so for part 2b, that indicates that it's about the same lever system, given that the mass at B is 1 kilogram. Okay, so right here now, that becomes 1 kilogram, and that's a mass. What mass would the block at C have to be to lift block B? So now I need that mass. Note, use the distance values above. Okay, so technically, masses are not forces, but I happen to know that both of these masses are on the Earth, so they'd have the force of gravity down on them. So if I wanted to prove that the mass is the force, I could turn it into a force. I could do force equals mass times acceleration. This mass is 1 kilogram. Force equals 1 kilogram times the acceleration in this case is the acceleration down due to gravity. And I know that the acceleration due to gravity is 9.8 meters per second squared. So 1 times 9.8 is a total of 9.8 newtons. Cool. So I can turn that into a mass. Now, what I'm really asking for here is use the distance values above what mass. So there's 2 ways to look at this. The first way is I could just kind of think logically. At B, the load here is 1 kilogram, and it's 4 times easier. So what would be 4 times easier to lift than 1 kilogram? It would be something that's 4 times lighter than 1 kilogram. So the first way I could do this, I could just say, well, it's 1/4 of a kilogram. So to be honest, that's how I would think about it. That it's 4 times easier. Since it's 4 times easier, it should be 1/4 as heavy. And that would be 1/4 of a kilogram, or you could also phrase that at 0.25 kilograms. It's the same deal. Now I could also prove it I could say, well, I know that mechanical advantage, right, is equal to 4. And I also know that mechanical advantage is equal to the force of the load over the force of the effort. And that the forces are proportional to the masses, right? Because force equals mass times acceleration. The accelerations are the same on both. So I could do mechanical advantage of 4 equals a force of a load, which is 1 kilogram, over the force of the effort. So I'm going to say mass of the effort here. Oops, that was a little bit messy. So the mass of the effort. There we go. And then when I solve that, I get the mass is equal to 1/4 of a kilogram. So that's convenient. It does, in fact, work out. All right, let's do number 3. What is the mechanical advantage of the pulley system pictured? So remember, when finding the mechanical advantage of a pulley system, you can count the number of pulleys. So I would count 1, 2. But wait, this rope keeps going around. So it goes around here, and it goes 1 right there. Then it goes up, and it goes 2 right there. Then it comes back down and goes 3 there. And then it comes back here and goes 4 over there. So it goes all the way around 4 times. Another easier way to do that would be just make a straight line through, and all of the ropes through the middle that are not the pull rope, so not this one that you're pulling on, but 1, 2, 3, 4 ropes going through the middle, mechanical advantage has to be 4. It's like a secret quick trick. All right. If you were able to exert a maximum downwards force, so if I'm exerting it, that means I'm pulling it. So I'm given the force of my effort, right? The force of the effort is 450 newtons. What is the maximum weight you could lift? So weight is a force. So I need the force of the weight or the force of the load. That's how much I could lift. The load is how significant the thing is. I need the force of the load. I have the force of the effort. And from up above, I also have a mechanical advantage. So let's use an equation. Mechanical advantage equals, the one with forces, is force load over force effort. Mechanical advantage is 4 equals force of the load over 450 newtons. To get rid of force by itself, I'm going to multiply both sides by 450 newtons times 450 newtons. 450 times 4 is 900 times 2, so that is the force of the load equals 1,800 newtons. So I could lift up to 1,800 newtons with that pulley system if I could pull down at 450. All right, let's do number 4, and then I'll let you keep rolling. Okay? For number 4, Ben Travlin, oh, what a hilarious name, physics, you go, carries a 200 Newton suitcase up 2 flights of stairs, a height of 6 meters. Then pushes, so this is a force. I'm just going to start marking them as I go. That's a force, and that is a distance. Then pushes it with a horizontal force. Okay, so that is a force, and a constant speed for a distance of 50 meters. That is a distance. How much work does Ben do on his suitcase during this motion? So I need the work. Okay, it says how much work does Ben do? And there's 2 sections here. First, there's the section where Ben goes vertically. Then there's the section where he pushes it horizontally. So I'm going to do 2 work equations. So work up is equal to the force up times the distance up. And the force up is 200 newtons, and the distance is 6 meters. So that's 200 newtons times 6 meters for a grand total of 1,200 newtons. So this section, the up section, is 1,200 newtons. Then the second part is horizontally. He pushes it horizontally along the floor, I think. Yeah. So now I'm going to do work. I'm just going to use a little sideways arrow. It's just a note to myself. Is equal to the force sideways. Oh, come on, oh, announcements. Times the distance to the side. So that is equal to 50 newtons is my force from over here times 50 meters. 50 times 50 is 2,500, and the unit would be joules. And I just realized in my first one, I used the wrong unit. I apologize. I need to get rid of that unit right there. That's not an eraser, but that is. There you go. And I got to replace that with joules. Wrong unit. Same deal over here. 1,200 joules. And up here, 2,500 joules. Okay, so then what's my total work? I'm going to take the two sections and add them together. I did 1,200 plus, then I did 2,500 for a grand total of 3,700 joules. Yay! Good job, Ben. I didn't do it. Ben Travelin did it. All right, number 5, I'm going to help you set it up, and then I'm going to let you go. So a person uses a lever to move a large boulder. I'm going to draw this one. Okay? So I have over here a large boulder, and I have a lever. There's my lever. The pivot on which the lever rests is 0.5 meters from the boulder. Okay, so there's my pivot. And I know that that is 0.5 meters and 2 meters from where the person grasps the lever. Okay, so I'm going to go out here and I'm going to put a little person. Hi, I'm grasping the lever. And that is 2 meters. If the person exerts 500 newtons on the lever, okay, so over here, the person has a force down of 500 newtons. How much force is exerted on the boulder? So we're asking how much force is over here. All right, so I got a distance, a force, a distance, a force. All right, force, distance, distance, force. It's on two sides of a lever. Hint, hint, that's really similar to our first one up here, where we did work equals work, force distance equals force distance. You give it a try, and then keep yourself going all the way through number 12, and then keep going and give it a try on 13, 14, 15. They're a little bit just like logical thinking. So don't worry about using an equation every time. If you can figure out like what's going on and see if you can logic it out, give it your best try. I think you got it. All right, have fun doing some problem solving, and I will post a key and go over it once you have submitted. All right, bye friends.